Ever stopped to think about how computers, those amazing machines built on just ones and zeros, how they handle something as basic as, like, a whole number?
Yeah, it's interesting, right?
It's wild. Today's deep dive, we're going deep into the world of integers in computer science.
Oh, exciting.
And we're breaking down excerpts from the Wikipedia article on integers.
Okay.
And trust me, it's way more interesting than it might sound at first.
It's easy to think, oh, computers, they just get numbers like we do.
Right. Just like
Uh,
intuitive.
yeah, but there's actually like this whole hidden layer of translation that's happening.
Okay.
It's a really cool system that dictates how computers store and work with numbers.
So let's unpack that a little bit. So we all know an integer when we see one, right? 10, 25,000, easy peasy.
Right.
But what makes an integer in computer science different from, like, the integers we use every day?
Well, imagine trying to like fit the entire ocean into a teacup. That's kind of what it's like. Trying to represent this infinite world of numbers in the limited space of a computer's memory.
So there's a limit. Computers can't handle crazy big numbers.
They can, but there are clever workarounds. We'll get to that.
Okay.
But for now, think of it like this. In computer science, an integer, it's not just about the value, like the actual number itself.
Right.
It's also about what we call its internal representation.
Okay.
How the computer actually stores it using bits, those zeros and ones.
Right, because to a computer, it's all just like on or off switches.
Exactly.
But how do you go from a string of zeros and ones to, like, the number 25?
Right.
That's where this whole bit width thing comes in, right?
Exactly. Picture a row of light switches.
Okay.
Each one is a bit, can be on, 1, or off, 0.
Okay.
Bit width tells us how many switches we're working with. More switches, more combinations,
Right.
more numbers we can represent.
So with one switch, two options, 0 or 1. With two switches, we could have 0, 0, 0, 1, 1, 0, 1, 1, 4 combinations, 0, 1, 2, 3.
You got it.
Oh, I'm seeing the light, literally.
That's the binary system for you. Now imagine 8 switches, 8 bits, or a byte.
Okay.
With 8 bits, we can represent 256 different values.
Wow.
And that's where we start diving into different types of integers.
Yes. The Wikipedia article mentioned all these byte, short, int, long. It's like an integer family reunion.
A little bit, yeah.
What's the deal with all these different types?
Think of them like different size containers for holding those numbers.
Okay.
A byte, like we said, typically 8 bits. Then you've got short, often 16 bits. Int, usually 32 bits. Each has its own capacity.
Okay. That makes sense. But why all these different sizes? Why not just use the biggest one all the time?
That's where things get interesting. It all comes down to efficiency and how computer systems have like evolved over time. Back in the day, memory was precious. Like every single bit mattered, literally.
So using a smaller integer was a way to save space, like picking the right size box to ship something.
Exactly.
But how does that play into the computers we use today? We've got gigabytes, terabytes of memory. Surely we can be more generous with our integers now.
You'd think so, right? But here's the thing. While our computers have become incredibly powerful, we're also asking them to do way more.
Oh, for sure.
Complex software, tons of data, billions of devices all connected.
Right.
And this is where those seemingly small decisions, those choices about integer size, they can actually have really big implications.
Okay, now I'm really intrigued. Are you telling me that something as fundamental as just choosing the right type of integer that can actually impact, like, the performance, even the way my devices work?
Absolutely. It's about finding that balance efficiency and also avoiding these things called overflow errors.
Overflow errors.
Yeah, that's a topic for next time.
All right, so we're back, and it sounds like we're teetering on the edge of, like, digital disaster.
Right.
Last time, we were talking about how choosing the right, like, size for your integers, it's like this balancing act.
It is.
So what happens when an integer gets a little too big? Like, is it a full-on computer meltdown?
Not a meltdown, but definitely some chaos, yeah.
Okay.
In computer science, we call this an overflow.
Overflow, so like a digital tidal wave crashing into the system.
That's a good way to put it. Imagine you have a glass of water.
Okay.
You fill it right to the brim. You keep pouring. There's nowhere for that extra water to go.
Right. Disaster.
It spills over. You've got a mess. It's the same kind of thing when an integer tries to use more bits than it has.
Okay.
Those extra digits, they overflow. And that can lead to, well, unexpected results.
So how disastrous are we talking? Like, what's a real-world example of what a little integer overflow could do?
Let's take a little trip back in time to 1996.
Okay.
Remember the Ariane 5 rocket?
Vaguely? Yeah.
Self-destructed just seconds after launch.
Right.
And the culprit. An integer overflow. A 64-bit number was trying to squeeze into a 16-bit space. And, yeah, not good.
Wait, hold on. A multi-million-dollar rocket literally went up in smoke because of an integer error.
Yep.
Okay, now I'm understanding why this matters.
Exactly. And it's not just rockets. It could be anything, really. A financial transaction, a piece of software malfunctioning.
Right. So software developers, they need to be really, really careful about choosing those integer types. But the article also mentioned that, like, the size of an integer type, it can vary depending on the computer.
Yeah.
So what's considered a, standard integer size these days?
You've hit on another tricky bit. What was standard a few decades ago is completely different now. It's like assuming everyone still uses a rotary phone.
So it's like trying to put a square peg in a round hole. Like, the code might work great on one system, and you try it on another, and boom, problems.
And that's why software portability is such a big deal. Developers are always trying to make sure that their code can run on different systems without getting tripped up by these little differences.
It's like speaking a language, but every region has a different dialect.
Yes.
Like, you might get your meaning across, but there's always a chance for miscommunication.
Yeah.
It makes you really appreciate all the hidden complexity that's going on every time you use technology.
For sure. And we've only scratched the surface. Did you know integers can be signed or unsigned?
Whoa.
It depends on if we need positive and negative numbers.
Okay, now that sounds really interesting. So it's like integers have this whole secret society.
I love it.
You've got, like, the eternally optimistic unsigned integers.
Right.
And then the realists, the signed integers.
Yeah.
Tell me more about this whole signed versus unsigned world. So, okay, we're back talking about the integer secret society. We've got the optimists, the unsigned integers. What makes them so special?
It's all about efficiency, really.
Yeah.
Sometimes you only need to deal with positive numbers. Like, think about counting the number of likes on, like, a funny cat video online. There's no such thing as a negative like, right?
Unless it's from my aunt who really hates cat videos. But yeah, I get what you're saying.
Exactly. So unsigned integers, they're like the specialists. They only handle the positive side of things.
Okay. So they can make better use of their bits, right? Because they don't need to worry about those negative values.
Exactly. It's like having a bigger container for all those positive numbers, since you're not reserving space for negatives.
I like the way you think. So we've got the positive vibes going with unsigned integers. What about those signed integers? What makes them so useful?
Signed integers, those are the workhorses. They can handle it all, positive and negative values. And that's super important for a lot of stuff. Temperatures, bank accounts, even just, directions on a map, north, south, all that.
Right. Makes sense. But how does a computer know if a signed integer is positive or negative? Is there like a little plus or minus sign hidden in the bits somewhere?
That's the cool part. It's all in how we interpret those bits.
Okay. So usually the leftmost bit, that's the sign bit. If it's a 0, positive number. If it's a 1, bam, negative number.
Wow. So one little bit, 1, 0, or 1. That's all it takes to decide if a number is positive or negative. That's wild.
It is pretty neat. And that brings us back to something you asked earlier, those really big numbers. Like, what happens when we need numbers so big that a billion looks tiny?
Right. You mentioned something about big nums and arbitrary precision, right? What was that all about?
See, that's the thing about computer science.
Yeah.
There's always a workaround. So for those massive, massive numbers, we've got special techniques.
Yeah.
These big nums, or arbitrary precision integers, they can actually grow.
It can.
Yeah. They use as much memory as they need to store those huge values.
So it's like a magical expanding container for those giant numbers.
Pretty much. And while there are, of course, limits to what even the most powerful computer can handle, these techniques let us work with numbers that are essential, like in cryptography or, when scientists are doing really complex calculations. You've definitely given me a new appreciation for these seemingly basic parts of how computers work. It's amazing how much thought goes into something as, fundamental as a whole number.
That's the thing, right? Even in something as simple as an integer, you find all this clever design, efficiency. There's even a touch of elegance to it, I think.
Totally. Well, we've covered a lot today, from binary and bit width to signed versus unsigned integers, even those mind-blowing big nums. So before we wrap up, why does all this matter? Especially to someone who's not going to go be a programmer.
Because tech is everywhere, right? And understanding how computers think, even just a little bit, it helps you make better decisions. Whether you're choosing a file format or thinking about online security, even just appreciating what goes into your phone or laptop, a little knowledge goes a long way.
So true. So next time we're online, sending files, even just checking our bank accounts, let's take a second to thank those unsung heroes, the
Yeah.
integers, working behind the scenes to keep everything running.
Absolutely. It
Hmm.
really is amazing. We've created these incredible systems all built on the foundation of integers.
Well said. All right, everyone, thanks for joining us for this deep dive. Until next time, keep those bits in line, and remember, sometimes the smallest things make the biggest impact.